Hello, my name is Bharat Suresh. I am performing my experiential learning for the subject finite element analysis. I am doing my experiential learning along with my teammate Raghavendra Sharma from B section. Our topic is FEA analysis and CFD analysis on an aircraft wing. So firstly, we'll make the aircraft wing on SolidWorks. To do so, first we'll open this website NACA0012 airfoils. We'll choose the chord as 1000 mm and download the CSV file of coordinates. The CSV file of coordinates is now downloaded on Excel, which we have opened. We add another, we have, as we can see, we have X and Y axis coordinates, and we'll also add a Z axis coordinate. We have opened this Excel sheet and we add this Z axis. We give the values as 0 for all terms, for all entities. Now, we open a new text document and we copy these values and we paste it in this text document and save it. Now we open SolidWorks and go to Features, Curves through XY points. We browse for those for our file. As you can see, the airfoil has been plotted. Now we draw a line over here to complete the figure, and we draw a center line in the middle. From here we draw some three rectangles with dimensions as follows. We fillet these parts and we copy this part into two more parts. We use linear sketch pattern for the same. Now, if we use the plane option, we choose the front plane for the first reference and we keep a distance of 500. We make 9 such planes. Now, we'll copy this sketch and onto all these planes. Now we've copied all this sketch onto all these planes. Now we'll do extruded boss base. The extruded boss base will be done for all features. The extrusion has been completed. Now we'll do surface extrusion by going on insert, surface, extrude. As you can see, the surface extrusion is complete. Now we'll hide it. Now again we'll do extruded boss base. We'll unselect the selected contours and we'll choose this portion. We'll choose up to surface. As you can see, we've completed the extrusion for this portion. Now we have to do the extrusion for the other two portions also. So as you can see, we've completed the extrusion of all these parts. And as you can see, the aircraft wing is now complete. Now we'll take this to
As we can see, start by taking the static structural into account. In Now in static structural, the engineering data is already loaded. We'll start with the model. The geometry we'll go to import geometry and we have made that geometry on SolidWorks, which will be shown later in this video. Now going towards the model, we will see how now we have opened the model geometry page and we'll do the different analysis and things in this on this aircraft wing. This is the aircraft wing that we have taken. Now we'll go to the geometry and change the material to and add titanium alloy into this. After adding the titanium alloy, we'll do the meshing by clicking on generate meshing. As the meshing is done now, we'll move further. Now the meshing is completely done. After that, we'll go to the static structural and insert the forces and loads. We'll enter the fixed support at one end, which is shown, and again insert the pressure at the other end, at the lower end. Now we have taken it as components and we'll define it only in the y direction as 100 MPa pressure. As we can see, the downwards direction pressure is there, and now we'll try to solve this. The solution is coming. Meanwhile, as we can see from the graph that it is the pressure is increasing from 0 to the 100. Now we'll find the total deformation and the equivalent strain and stresses. We are finding the total deformation, equivalent elastic strain, maximum principal stress and strain energies, and the total deformation. After inserting all the solutions into it, we will finally solve this analysis, solve and find the analytical solution of it. As you can see, the total maximum deformation, static structural, total deformation on static structure, and the various stresses and strains acting onto it. This is the equivalence elastic strain. Again, the maximum stress is 2274.9. The equivalent strain, the maximum principal stress acting, and the strain energies at various parts of the aircraft wing. Also, we have found the total deformations, which we can see is the same in all the cases. Hence, the solution, and this is the simulation of what we have done, and the frequency and different modes of it. The modal analysis. We can check it out by different ways, and we can see according to the color combination what and all are the forces acting onto the aircraft wing, and what is the deformation at different places. Now we will move on to the CFD analysis.
Now, coming to the fluid flow, we'll firstly choose fluid flow fluent. We'll import the geometry. We'll choose the aircraft wing. From here, we'll edit the geometry now. The window is open now. It's taking a little time to open up. Yeah, as you can see, we have the aircraft wing in front of us in fluid fluent in the design modeler, and now we'll uh, make a rectangle around this. This will help us in doing the the CFD analysis and the and determining the fluid flow. We'll choose the constraints in such a way that the distance from the aircraft wing is about 1.5 meters. As you can see, the distance is fixed at around 1.5 meters. We have generated the solid. We're going to rename the solid as the wing. You can see the model as you in the design modeler mode. Now we'll add some Boolean values to it. We have selected the operation subtract, and we have chosen the body for as the target body. The tool body is also selected. and we'll generate. As you can see, the new body is being made with the aircraft wing inside the rectangular block, and on this we'll conduct further evaluations. Firstly, now we'll mesh the solid body. As you can see now that the body has come up in the meshing mode, we'll start choosing surfaces. We've chosen selection. Now we'll apply meshing on the entire body. We'll choose one of the faces as the inlet and one of the faces as the outlet for the air to flow, and which will give us the CFD analysis of the wing. And the other parts we'll choose it as walls where the flow of the air will not be happening. This the we have renamed the cutout portion as the wing. We'll choose the default. We'll choose an element size for the meshing about zero point 0.6, and now we'll generate the mesh. As you can see, the meshing is now complete. From here now we'll move back to the original window and update the meshing. Now we'll move to setup to calculate the drag force coefficient. We'll choose fluid launcher. The window has opened up for fluid launcher. In this, we'll now input our values of air to be flown in, the velocity, and plot graphs and find out the drag force coefficient. As you can see, the object has been imported, and as you can see clearly, the one of the faces has been chosen as the inlet, where the air will be flowing through, and the other side has been chosen as the outlet. And the inlet air will flow through the wing of the aircraft and move out through the outlet. And now we'll be choosing viscous forces. We've chosen K epsilon and also enhanced wall treatment. From here, we'll choose the fluid, with, like I said, we'll be choosing air, and we'll choose the viscosities. We've chosen, now we'll be looking out after the boundary conditions in the inlet. We'll choose the velocity magnitude as 8.163 meters per second. We'll choose reference values. We'll compute from the inlet towards the outlet. We'll use report definitions for finding out the values of drag coefficient. The report definition will be made on the wing. Now we'll be finding out, and apart from this, we'll also be finding out the lift report definition. Now we'll do the initialization. We'll choose the number of iterations as 25. That is the number of times the air will be hitting the wing. That will be the number of iterations. As you can see, the graph is now being plotted. With successive iterations, the nature of the graph is continuously changing. The calculations by the computer is now complete, and as you can see, this is the graph that has been plotted. The CD values has been found. The graph can be seen as shown. Now we'll go to report definitions and show the report, the results and the calculations that we have found out. We're gonna, like I said, we are going to compute the lift coefficient, and as you can see that the values are visible. We got around 0.468, and the drag coefficient is also found. The drag coefficient has come about 0.036372569. Now we're going to find out the vectors, the velocity vectors, which is now visible like this. This is the velocity vectors on the aircraft wing. The magnitudes also are visible. The highest is around 1.26 into 10 1 point, sorry 12.6 meters per second.